Okay, so 1.5c is about stretches and compressions. It's about if we multiply or divide our variable, whether it's on the inside of the function or the outside of the function. Okay, so the first one, vertical stretch or compress. If there is something multiplied on the outside of the function, it will change how far away the function is from the x-axis, the stretch of it up and down. So if a is greater than 0, it's going to stretch away from the x-axis. We call that a vertical stretch. If a is between 0 and 1, so if it's fractional, a proper fraction, so 1/2, 1/3, 2/4, 2/5, something like that, it's going to compress it closer to the x-axis, so it's a vertical compression. Now, I didn't include when a is negative because we know what a being negative on the outside does, hopefully. In 1.5b, we talked about how that flips it across the x-axis. Okay, so that does not include the negative. The negative has its job. It flips it across the x-axis. But if a is more than, let's actually make that, more than 1. If a is more than 1, it's going to stretch it away from the x-axis. If a is that fraction, it's going to squish it down closer to the x-axis. So a vertical stretch or compression changes the distance from the x-axis. Okay. So it changes how far away from the x-axis we are. Now, unlike the ones we had done in 1.5a and 1.5b, those, I think, are kind of a little more intuitive of what happens. These ones you may have to actually plug in points, which is not something that I encourage because we want to try to get away from that. But the distance away from the x-axis is a good way to think about it. That will help. Now, the one that's weird, anything we do on the inside of the function always does the opposite of what we think. If b here, touching the x, is bigger than 1, it is a horizontal compression. It is going to be closer to the y-axis. If b is fractional, so between 0 and 1, it is a horizontal stretch. So this one changes the distance from the y-axis. They always on the inside do the opposite of what we would expect mathematically. They always do the opposite of what we would expect mathematically. So it just has this opposite way about it when we're touching the x. If we're on the outside of the function, it kind of will do what you think it does, and so it's really nice. But inside the function, it always kind of does the opposite of what we want. If you multiply by 2 on the inside, it is going to actually squish it inward. If we divide by 2 on the inside or multiply by 1/2, it's going to stretch it outward. It'll look wider from left to right. So it's just weird. And sometimes for this section, again, we might have to plug in some points. Okay, so let's look at our first example as asking what has happened from the function, how can we describe the transformation? Well, if there's a 2 on the outside, it's going to double the height away from the x-axis. So it's going to double the height, and it is technically called a vertical stretch. It's a vertical stretch. But if there's a 2 on the inside of the function, it is going to make it, it is going to compress it inward. It's going to make it closer to the y-axis. It's technically a horizontal compression. So it's kind of hard to really describe these as much until almost you need to graph them and verify that's what happened. So that's what we're going to do in example 2. We'll graph each one of these things and kind of verify that that's exactly what happens. Now, let's draw for this one our parent. Let's call it g of x. Our parent is the cube, the cubic function. And you might recall that it looks like this. Very stretched up kind of parabola sort of shape here, but very thin. And then it has a piece matching down here in the third quadrant. So that's what the parent looks like. Now, this function has not moved left or right at all. So for f of x, I would suggest plugging in those 3 good points, -1, 0, and 1. And we should expect that the height is doubled, that it is stretched outward or upward. So remember, we said that it was a vertical stretch, an upward stretch. If you plug in -1, you get 2 times -1 cubed, or 2. If you plug in, let me make that a different color. If you make that 0, 2 times 0 cubed is 0. If you plug in 1, you get 2 times 1 cubed, which is 2. Okay? So let's draw the new f of x function next to our parent function, and let's see, it's like we pulled those strings, those arms, and it should be a little higher than we expect. Well, 0 is still 0. At +1, now we're at a height of 2. At -1, now we're at, I'm sorry, that's -2. Now we're at -2. And so you can see that it's a little bit steeper, or if you could imagine taking the red strings, if they were made of string, and pulling it so that it is double the distance away, it's higher. So you can see it's higher here, it's lower, I mean it's further away from the x-axis, okay? So anytime we multiply on the outside of a function, it affects its height. If we multiplied by 1/2, if it was 1/2 of x cubed, it would be squished closer to the x-axis. So it's sometimes a matter of plugging in some points for those. Now let's draw d, which is the square root of 2x. So let's make the square root function, and I'm just going to graph it on here. The parent, let's call that just the normal square root. Now the normal square root is 0, 0, 1, 1, 4, 2. Those 3 are good. Okay, so that's the normal parent. But the problem with something on the inside is you really have to think about what numbers will work. So you have to ask yourself, when will 2x equal 0? When will 2x equal 1? When will 2x equal 4? Because those are the nice perfect square roots that we want. So where will the inside of the square root equal 0? Where will the inside of the square root equal 1? Where will the inside of the square root equal 4? So that's going to be 0 divided by 2, 0. 1 divided by 2, 1/2. And 4 divided by 2, or 2. So if I were plugging into this function, I would plug in 0, 1/2, and 2. Because those are perfect squares. Those are going to give us the perfect square. So if I plug in 0, I get 0. If I plug in 1/2, I get 1. The square root of 1 is 1. If I plug in 2, I'm plugging it right here. If I plug in 2, I get the square root of 4, which is 2. So let's do that. I'm going to do that in like a, well, what color have we not used? Let's do purple. Let's do that in purple. Okay, 0 is at 0. 1/2 is at 1. 2 is at 2. Would you notice how the purple graph is closer to the y-axis? See how it's closer to the y-axis than the green graph? The green graph is stretched further away from the x-axis. That's because that was a horizontal squish. We've squished it in closer to the y-axis. So that's what a 2 does on the inside of the function. It makes this distance half as much. See? So this distance is half as much. This distance is half as much. This distance is half as much. This distance, so the distances, it gets squished in. They're the hardest ones to see, so they will be ones that you might just have to plug in points. Okay. And then one last one, and then you'll have the rest of class to work on the homework. Okay. So can somebody tell me what is the parent function for example 3?
Square.
A square, a quadratic, that's okay. So our parent, that's okay, is y equals x squared. So let's always draw the parent. So that's what we know the parent looks like for this particular function. Now let's look at, there are 3 things that have happened to this function. Okay, there are 3 things that have happened to this function. We have a negative on the outside. Okay, so a negative on that outside is going to flip over the x-axis. Okay, so we should expect that. A 2 on the inside should make it closer to the y-axis. So it should look skinnier. So it's closer to the y-axis. And do you remember from Monday, from 1.5a, what does a subtraction on the outside of a function do? Anybody remember? If we subtract 1 from the outside, on the outside, where does it go? If we subtract 1 on the outside, where does it go? Yeah, it's going to go down 1 unit. So 3 things are going to happen to this function. It is going to be flipped over the x-axis, skinnier than normal, and it is going to be down 1. Okay, so what's nice to expect that is helpful. I'm still going to plug in, let's plug in -1, 0, and 1, okay? Because we haven't moved left or right at all, so usually just plug it in those values. The only one you really have to be concerned about plugging things in correctly especially is the square root, because there's only perfect squares of certain numbers. But okay, so if you plug in -1, you get the negative of -2 squared minus 1, okay? Following order of operations, we got to square that first, right? That's going to give us 4. So we're going to get -4 minus 1. We're going to get -5. Okay? If we plug in 0, we get the opposite of 0 minus 1, which is -1. And that middle value has moved down 1, which is a good sign. And then because of the good old symmetry of a quadratic, these 2 should come out to be the same number. If this is the center, these 2 should match. And so if we chose right, those will match. And so if I plug in 1, I get 2 squared minus 1, which is negative 4 minus 1, or negative 5. See how they match? That's what's nice about a quadratic. You can kind of check your work because it's going to do that every time. Okay, so at negative 1, we are down at negative 5. At 0, we are at negative 1. And at 1, we're also down at negative 5. Okay, so let's compare the red one to the purple one. In the reddish one, the graph is flipped over the x-axis, right? It's pointing downward. It's skinnier than the other one. Not by much, but it's skinnier. And has it moved from the center at 0, 0 down 1? Yes. So we should expect as we go and as we put these things together that those things should happen, okay? Okay, so you will need graph paper. There are 10 graphs, okay? What I want you to do for each one is name the parent function, describe what you think is going to happen, and then graph it. You might need to plug in some points for these to get an accurate graph. There are 10 of them. We don't have anything else planned for tomorrow, so you can work on it today, you can work on it tomorrow. There you go.